So I'm Lohit. I work for a company which builds the platform to serve public conversations. It's Twitter. Or simply put, as Youb says, we send a lot of messages. So in this talk, we'll describe Twitter's data replicator architecture, how we extended it to Google Cloud, and maintain the same interface for our users. Our users are the internal developers or all the users within Twitter. At any point of time, if you want to ask questions, you can always tweet to the hashtag, hashtag GoogleX19 Twitter. A lot of our team members are here. They can answer it. Or I also have time towards the end of the talk. So before getting into the actual replicator, I want to spend some time around the data infrastructure we use for analytics. So at Twitter, we primarily use Hadoop for large-scale analytics. Hadoop distributed file system, HDFS, is our primary storage. We have multiple clusters, large clusters, which can host up to an exabyte of data. There are multiple clusters per use cases. We have production clusters, ad hoc clusters, and each of those clusters have different properties and also machine configuration based on the use case to make sure we always optimize both the jobs as well as the cluster utilization. So this is like a diagram of how the actual data flows at a very high level. So whenever users use Twitter.com or use the Twitter mobile, their actions generate a lot of events, what we call as events. We generate about like 1.5 trillion events every day. That's about 1 billion events every minute. So all these events flow through a system called a log pipeline. So whenever the events, each of these events have a name associated with that. So the log pipeline is responsible for aggregating all the events for the same name and write them as log files on HDFS. We call this as the real-time HDFS. This acts like an incoming HDFS. And usually it does like a lot of cleansing, format conversion, and then also does a time order partition, like year, month, day, and hour. So all the events which got generated from like thousands of different endpoints end up as log files for that particular hour in the same place, right? We call this real-time Hadoop cluster is because this is the entry point for our log files. The SLA on these clusters are like very high. This cluster has been up for several years for us. We always do rolling upgrade. From there, once the data set gets collected as hourly partition, users would have configured, okay, which cluster that those data has to be replicated. So it can be replicated to production or ad hoc clusters based on the data set and the configuration. And then once the data lands on these clusters, they run more jobs on that and generate even more data sets. So, and those data sets can also be configured to be replicated to either like a cold storage or production use cases and all those things. Apart from our like batch analytics, the log pipeline will also stream some of the events for our real-time computing. So we use Apache Heron for our real-time computing framework. So today, overall in our clusters, we crunch like hundreds of petabytes of data every day across like thousands of jobs running every day, right? So when you look at one of the cluster, right, what is in a cluster, right? So in a cluster, you will see many data sets, and a replication service is responsible for replicating that data from somewhere, from source to this cluster. With every data set, there is also a retention associated with it. So we have a retention service which takes care of deleting the data based on that data set's configuration. We have multiple different compute frameworks like Scalding, Presto, Hive, like MapReduce jobs, which crunch the data and do analytics. So they interact with a system called DAL, or Data Access Layer, which is like our metadata service. So the DAL has information of all the data sets and the partitions, hourly partitions associated with that data set. Whenever a replication service copies a new data set, the DAL is again updated. We also have a front end for the DAL, which we call Eagle Eye, which gives a global overview of any particular data set at Twitter. So a data set will have a logical name, and it will have multiple physical locations. So which means that same data set is available at multiple different clusters. And we'll also have like different properties associated with them, like schema, owner, what kind of data it has, like whether it has PII data or such, right? It also has information about whether this data set is hourly partitioned or a daily partitioned and such. So there are some more information in some of the blogs about this. So I also want to touch upon, we are like now talking about like a lot of data spread across many different clusters, right? Like how do we identify this? So traditionally, people who have been using Hadoop know that when there was one HDFS, you used to refer to the data inside HDFS using HDFS:// a name node name and a port and a path within that. Then came multiple namespaces and HA. So with that, the open source community introduced the concept of view file system. View file system is a client-side mountable where the client will resolve which particular name node it has to redirect the requests to. So this way you could scale multiple name nodes and also add in like HA for the name nodes. So you would refer something like viewfs:// and then cluster X, and then the data within that. In this example, we are following /logs/partlycloudy. Partlycloudy is also the project name which we use for this effort. At Twitter, as I said, we have multiple clusters and multiple data centers. So what we ended up doing was to extend that view file system to add, we call it something called as a Twitter view file system. With this, what you can do is you can globally identify a data which is stored in any cluster. So you would say /datacenter1, cluster X, and then the data, and the client-side mountable will take care of resolving it to the right Hadoop name node. So now what happens is that the tools such as a replicator will use these globally identifiable paths and then act upon the data which it's replicating, right? So like what is the need for replication? As I said, like we have multiple different clusters. This is just a snapshot. As you can see, we have thousands of different data sets people configure, and they needs to be kept in sync, like not just one from source to destination, but there is source, destination, back, and then there is also merging, right? When you say replication, at the very high level, we have two kinds of replication. One is a source to destination. It's a 1:1. We always make sure that any new data which gets generated in the source has to be kept in sync with destination. And we could also have configuration wherein you could have multiple sources, and all the data belonging to that particular R has to be merged and made available at a destination. So this is like a copy plus merge. So when users set up a replication, right? So typically what they do is they provide a data set name, like a partlycloudy as a data set name. They provide source cluster and source path, destination cluster and the destination path, and some other properties associated with that, and then add it to a metadata layer such as DAL. Replicator would fetch that entry from DAL and basically translate it to saying that, okay, data set partlycloudy, and this is my source globally identified path and globally identified destination, right? So what is actually replicator is actually doing? So a replicator is like a long running daemon, which we run it on frameworks such as Mesos, so that even if the node goes down, like Mesos can actually automatically start that replicator somewhere else. It's completely stateless. Whenever it starts up, it queries DAL and then asks, so give me all the configurations which is responsible for a particular destination cluster. So we run one replicator per destination cluster. So it is responsible to make sure, in making sure that all the data sets from different sources are in sync at the destination cluster, right? So after fetching those entries, for each of this entry, it will do a metadata lookup from the source cluster to destination cluster. Basically, it does a directory listing to make sure like all the partitions are in sync. If any new partitions are available, then it kicks off a MapReduce job called Hadoop DistCP job. And DistCP job is the one which is actually transferring the data. The red arrow shows transferring the data, and then DistCP job writes locally at the destination cluster, right? As you can see, the source path is cluster X logs partly cloudy, and then there is an R, and the destination would be translated to the globally identified path here. In cases of where we have to merge multiple data sets, this is for data sets, as I said in the very beginning, the incoming data lands on RT clusters, right? So we have that set up on multiple different data centers. So for an developer who needs to access data for a particular hour across all our data centers, we need to make sure that we merge for that particular hour. So in this case, what happens is the replicator identifies that this data set is of type multiple sources. So it will kick off one DCP job per source to destination independent. And once it is done, it will merge all of them into a temporary space and then does the final atomic rename. So once after this is done, it will make a call to DAL to saying that this particular data set at the destination cluster for that particular hour is now available. So all the tools who have been waiting on the new data can automatically start consuming the data, right? So when we decided to migrate some of our workload to GCP to unlock new features on GCP, so we started looking like what all data needs to be replicated to GCP. And just like the previous configuration, this was even more complicated. Like the data was spread across multiple different clusters, and we had to replicate all of them to GCP. And once it lands on GCP, like we could unlock like a lot of tools such as Presto on GCP, Scalding, like Hadoop clusters on GCP, BigQuery, all the data which gets replicated to GCS can be loaded into BigQuery, and then unlock all these different possibilities. So what did we do? Like we tried to see how did we do this, right? So remember I talked about the view file system, Twitter view file system. So to access the data which is stored in Google in GCS, which is buckets in GCS, you use something like this, gs:// and then bucket name logs.partlycloudy. So there is also, Google has open sourced this library called Cloud Storage Connector. What it essentially is, Hadoop file system APIs is like a abstract file system, and all the other file systems can implement those interfaces. Like HDFS is actually an implementation of that file system. So Google has implemented the same interface to provide the file system abstraction for the additional upper layers. So anybody who is using the file system APIs can transparently access Google Cloud Storage as if they are using some like Hadoop commands. So all the Hadoop commands, the jobs which you run, everything will run as is. So we plugged this one to our view file system as a mount point. So what we did was any path in Twitter which refers to /GCS will automatically translates to buckets on GCS using the Google Cloud Storage Connector, right? So let's look at what is happening with the replicator. So for most part, we didn't have to change too much in replicator code because it was using the Hadoop file system APIs. So, but what we ended up doing was, as our other replicators, we run GCS replicator per destination. We created something called as a copy cluster, which acts as a destination, and set up a replicator for GCS alone. So this copy cluster has all the GCS mount points as I described. So any data which gets written to /GCS is transparently getting redirected to Google Cloud Storage buckets. So when you are replicating a input data set from a cluster X to a destination /GCS, what is happening is the DistCp job is transferring the data from the source cluster and using the cloud storage connector, it's writing the data directly to buckets on GCS, right? So for this to happen, we had to do a few things with the network. So as I said, the replicator does two things. One is the metadata operation, which is like it compares the source directories and the destination directories. So for that, we used a proxy to reach the Google endpoints, because the amount of data which gets transferred around metadata operations is not that much. But the actual data is in the order of petabytes. So what our network engineering team did was to create this Twitter and Google PNI, private network interconnect, so that all the worker nodes in our copy cluster have direct access to the Google endpoints. So now any jobs which are running, any tasks, DistCp jobs which are running on copy cluster, whenever it has to write some data, it can directly write to GCS for us. Apart from that, Google also has this concept of multi-region bucket, and while we were doing this testing, they introduced dual region buckets, wherein any data you write into those buckets are only available in 2 regions, and from either of the 2 regions, if you write, it will be automatically available to access from the other region. So our network engineering team also created that PNI setup for the data centers. We have multiple different data centers. Whichever was closer to the region, they created that interface. So now for cases of n:1 copy, where we have multiple sources writing into a destination, we can set up DistCp jobs independently, and they can write, all of them can write into the same path as at the destination. So we also did this because renames on HDFS is pretty cheap, because everything is, you have a name node, but on an object store, it was pretty expensive. So for this particular DistCp jobs alone, it understands that they are writing to GCS, so they try to write in place, right? So now, how do you guarantee consistency in that, in this case, right? So in such cases, what we did was, this shows a state diagram of how 2 replicators with multiple different sources writing to a single destination achieves consistency. So each of the replicator basically kicks off its part of the copy, and all the files have a data center name embedded in them. So there is no name conflict to begin with. So once the copy is done, each of the replicator will create a underscore success and the source data center name in there. So once it is done, like each of them independently will check if all underscore success have been found. If they are found, they will make a call to DAL to say, hey, the data set for the merged data set is available on GCS. Even if there are multiple updates to DAL, it is okay. So these are idempotent operations. So we are okay in such cases, right? So with all this setup, right? So how does it look for our users, right? Like one of the goal is to make sure that if we have a uniform access for our users. So Eagle-i, as I said, is a front-end interface for our DAL. Whenever we are replicating to GCS, we are also publishing those partitions in DAL. So this Eagle-i, if you see for a particular data set, logs, partly cloudy, there are multiple different locations, physical locations, DW2, HDFS, Hive, and all. And now GCS becomes just another destination for them, right? So for them, like the data is in HDFS as well as GCS, and you also have a graph which shows the latency of copying each partition to GCS, just like how we have for our HDFS clusters. So DAL provides a lot of APIs to identify, like for a particular data set, what are all the partition. It also has like command line tools. Now, if you were to query, okay, show me a logical data set name called partly cloudy, you get an entry. And when you actually look at all the physical locations for that, you can see there is one is HDFS and one is GCS. So it's the same interface, same APIs for our users who have been using DAL. And you can query all the partitions for that particular data set at a particular location. So it will give you hourly partitions. As and when replicator is copying data, it is also publishing this information to DAL with a uniform interface for our users, right? Not just users, like for ourselves or our SREs. So since it's just another instance of replicator, we use the same monitoring tools. So in this case, we are showing for a particular category what is the read-write bytes and what is the latency of replicating from source to destination. So one of those colors is basically just another cloud replicator for us, right? We have also like comprehensive alerting for our existing replicator. The same thing translated for the Google replicator as well. We have one and if there is like some problems, for example, in the bottom graph you see some DCP jobs are failing, so we can configure rules which will say pages if you cross some threshold, right? So as part of organizing all the resources in GCP, tomorrow morning there is an excellent talk from our teammate Vrushali, who is going to talk more about how we organize our projects and resources and users into different GCP projects. So you should definitely check it out. So essentially we have on GCP, we have different projects per different organization. Now we took advantage of that and said, okay, we'll deploy different replicators per project so that, and these replicators are going to be using separate service account, credentials, and all those things, right? So all the data which is owned by a particular organization that replicator will be responsible for replicating the data. So if you have problems with the keys, you just have to like rotate the keys for that particular replicator. Or if you want to do some updates or testing or anything, right? So you just adding another more replicator for that, right? We also did one more thing. As I said, in the Twitter view file system, it's basically a client-side mount table to say if you have if you have two namespaces, you would have two entries saying that anything which starts with a prefix go to first entry, if not second. But with GCS, what happens is we'll be managing like thousands of users, which translates to thousands of buckets. And also you'll have like hundreds of categories, right, or data sets, which translates to hundreds of different buckets. So instead of like creating hundreds of entries in the client-side mount table, what we ended up doing is to implement a regular expression-based client-side mount table, wherein the paths such as /GCS/logs/partly cloudy will translate to gs:/logs.partly cloudy. We also are maintaining a well-defined naming convention for our buckets. So this makes it very easy for us to do this regex-based conversion, right? So with all this setup, right, like where are we today? Like we have tens of different instances of these replicators per project, per test setup across multiple data centers which are running. We have copied like petabytes, tens of petabytes of data. Like many use cases have been unlocked, like BigQuery, Presto on GCP, and all. And like there'll be like a lot of blog posts coming coming soon about all those things. And so this effort was made possible only with close collaboration with folks at Google. So while we were testing this out and then doing some iterations, there were like a lot of enhancements for the Google Cloud Hadoop connector. For example, when we started off, HDFS has a different checksum than GCS, right? So if you run a DCP job, even though the data is copied successfully, it will check the checksum and says there is corruption, and then it will rerun the job again. It will delete everything and then rerun the job again. right? So when we talked with the Google engineers, they identified this and then they started to make changes to the Hadoop code itself to provide a flexible checksum option, which is now open source. There is also a blog post about that. And while that was happening, we also made modifications to our DistCp jobs to do a streaming checksum until this was deployed. There were like various other enhancements for the replicator, such as proxy configuration as a path to a file instead of like encoding username and password of a proxy credential. Because what used to happen is that used to get loaded into configuration object, and once in Hadoop land, once it is in configuration object, it gets passed around everywhere, right? And also, when we started off, Google had only a way to specify one user credentials, and then we changed it to per user credential. Whoever is running the command, we can dynamically pick up their credentials to access GCS. And when we were integrating with our view file system, like lazy initialization support for the Google Cloud Storage. Apart from that, we have other teams who are also evaluating a lot of stuff on GCS, for example, Presto. So they discovered like a lot of performance improvements, so which translated into changes both at our end, open source Presto community, and also GCS. So this was a very good collaboration. There will be some blog post and lot of things around the Google Cloud Storage connector, especially for the object store, right? Because we have been used to using HDFS, and our applications are used to thinking in a HDFS kind of way, wherein renames, for example, are atomic. But that is not possible on GCS. So Google folks implemented this cooperative locking, wherein if you turn on that flag, if multiple people are trying to do a rename, then it will take a lock and do a rename, and then there is a FSCK for recovery and all those things, right? And in most of the cases, what we do is we try to, whenever these stuff are open source, we try to use the same version as much as possible. That also makes it very easy for us to report any like support cases. Whenever we file a support case with Google, we can just say the version which we are using, and they can refer to the open source version and say, okay, this is what was happening. They can refer the code. So that makes it very easy, right? In summary, I think I hope I was able to explain the replicator architecture while extending it to the Google Cloud and maintaining the same consistent interface for our users. I also want to acknowledge few of our team members. A lot of people worked on many different components of this. And this special link, cloud.google.com/Twitter, where there will be a lot more information and blog posts and linking, cross-linking and such. Finally, we have a lot of openings across the board, and I encourage you to tweet or apply online